is founded on the works of 6 famous mathematicians, the lives of which and the contribution to the modern geometry will be the topic of our lesson for today. The non-Euclidean geometry introduction will revolve mainly on the history and some introductory topics on the various forms of modern geometry. Let's begin. In this lesson, the big question that we're going to answer is, what is non-Euclidean geometry? Specifically also, we're going to dig deeper into the questions. Who is Euclid? What is his geometry? What is classical geometry? And why do we need to come up with a different geometry than the geometry of Euclid? Why the need for modern geometry? Is classical geometry not enough? Is modern geometry more fit to our times? We're going to find out.
Sir, gasagarak po, sir.
One moment. Try to fix the microphone. Hello? I'm sorry. I think there's a static in the aircon here. Now let's go back to the lesson. I'm showing you a famed city of Alexandria. Alexandria is one of the 3 big cities of Egypt. One is Cairo, another is this, Alexandria. The third one is Giza. Is it Giza, sir? Yeah, it's Giza, famous for its pyramid. This one is also a famed city, a very big city in Egypt. We call it Alexandria. For the participants of the lesson that we had last Tuesday, can you tell the class why this city is called Alexandria? Anyone? Yes, someone's
Sir?
raising a hand. One moment. I'm going to read the names of people raising hand. We have Ivan June. Yes, Ivan?
Sir, Alexandria was founded by Alexander the Great, famous in Alexandrian Lighthouse. It is the city
Very
of
good.
Euclid, who developed geometry.
Okay, so that's more information that's intended. Now, the one that you're looking at is a city founded by no other than Alexander the Great. And the reason we're talking about it is because this is the city where Euclid has stayed most of his life. This city is famous for the Alexandrian lighthouse, once then considered one of the wonders of the world and was destroyed along history. Most of the people of Alexandria nowadays petition for this lighthouse to be restored, but until now, it has never been restored. Maybe political reasons. We don't know. We're Filipinos. We're in the Philippines. Anyway, the one that you're looking at the right is the father of geometry. When we say geometry, we're mostly referring to classical geometry. This is Euclid of Alexandria. This needs to be mathematician, while Euclid of Alexandria is the father of geometry. It's important that you know the difference because it may appear as a question in the licensure examination for teacher, and you may get confused with Euclid of Megara with Euclid of Alexandria. So you need to associate Euclid with the city of Alexandria.
Sir, gawara-wara po, sir.
Now, you need to remember as well the famous work of Euclid. Who can remember the work of Euclid? Did we mention the name of the work of Euclid before?
Wara man, sir. Ang ilang ging sulat, ang 13 books, sabi mo. Ang definitions, propositions, probability.
Okay, so there's a name for that. The name of the work of Euclid, I'm going to write in on your screen, is the elements of, this is how we spelled geometry before. Geometry. But nowadays, you're going to replace the IE with a Y. And some people would only remember his work as the elements. But the full title of the work is the Elements of Geometry, composed of treatises, proven axioms in geometry. Now, who can remember Hello? Hello? Now, who can remember the number of books in the treatise, in the Elements of Geometry? Christian Joy? Yes?
I think po,
13
sir,
books.
13 books, 300 BC, sir.
Very good.
13 books.
There are
Thank you.
13 books in the treatise of Euclid of Alexandria. That's why he's called the father of geometry. Now, before we proceed, let's just explore this basic information that you need to know before we dig deeper into geometry. Geometry came from two roots. Who came first? Anyone? We have Ira. Yes, Ira? The first one is?
Geo means earth.
Very good. Geo means earth. The second one? Anyone?
Metry.
Yes, Chris?
Sir,
Yes? What's the second one?
metric po, sir. Metric for
Metric or
measurement.
metrion, which means
Measurement.
measurement. Now you need to remember this. The two roots of geometry is earth and matter, because later on we're going to talk about them when we talk about the life of one of the mathematicians responsible for modern geometry. Let's talk about them. Modern geometry has been made possible because of the work of 6 mathematicians. Namely, we have Carl Friedrich Gauss, Nikolai Lobachevsky, Janusz Bolyai. Janusz Bolyai has another name. He's known also as Johann Bolyai, Eugenio Beltrami, Felix Klein, and Henri Poincaré, a French mathematician. The first one that we're going to talk about is, we have here, that's the face. That's Carl Friedrich Gauss. I think, Carl, you have a problem with your internet connection. Okay, so Carl Friedrich Gauss is, you know what, he's actually the main player in this story. His work has made everything possible in modern geometry. He is a great mathematician from Germany, and he is considered the Princeps Mathematicorum, or the foremost of mathematicians. And he's considered the greatest mathematician since antiquity, whose importance falls only below Newton, who co-developed calculus, and Euler is one of the most important persons in modern geometry. Now, Gauss was the dominant mathematician of the 19th century. When we say 19th century, we're mostly referring to the age or the year beginning from 1800 to 1899. That's 19th century. And he took the reins after Euler and Lagrange. His work is mostly following the work of Euler and the work of Lagrange. And as I mentioned before, he ranks only below Euler and Newton in the pantheon of mathematicians. He's one of the, given a chance to go back to history, if you're really a serious mathematician, he's one of the mathematicians you're gonna visit, because at an early age, he already demonstrated a keen sense for mathematics. In fact, there's a movie made after him. And as a trivia, the name of the movie, if you're going to translate it in English, is To Measure the Earth. That's a play in the word because he co-developed modern geometry, geometry, earth measure. And the title of his movie is To Measure the Earth. Now, the movie opened with a scene of him being one of the students in a class. I don't know, but they look like 6 to 8-year-old boys. And there's a strict-looking teacher in front, writing on the blackboard a problem that they're supposed to solve. And judging from the reaction of the children, it looks like there's a competition on who could answer the problem first. The problem goes like this. The teacher wrote 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. And then he told the class, do this until 100. Now, the usual response of the kids who want to answer it first, they were all writing on a piece of what looked like a small version of a blackboard, a chalkboard on their hands. They're solving it, and they're trying to come up to the sum up to 100. While Carl Friedrich Gauss was dreamily looking at the board, not doing anything. He's not even solving. And what happened is, one moment. I need to pause this. One moment. I'll go back at you. Someone important came. Okay, going back. Now, Carl Friedrich Gauss, as a kid, was dreamily looking at the board. And the teacher was a bit not happy about it. Minutes after, Carl began writing on his own board, And after a few seconds, perhaps, or a few minutes, he is ready with the answer. He gave it to the teacher, and the teacher was dumbstruck. He was angry because he was thinking Carl was cheating. So he asked Carl what he did. And he demonstrated it in the board. What he did is he wrote the numbers forward first. 1, 2, 3, 4, 5, 6, 7. And on the second line, he wrote it backward. 100, 99, 98, 97, 96, something like that. And he demonstrated that the sum of each of the pairs is always 100 all throughout, the number line. So postulated there must be 100 sums of 100. To get the sum, since he wrote 2 lines, he divided it into 2, giving him 5,050. And he was correct. And he's actually the origin of such a method. Are you angry, my friend? Okay, let's proceed. So that's Carl Friedrich Gauss. And that's how brilliant he was since he was a child. Now, if someone of you has given a thought about that, like if you want to add numbers forward consecutively on an arithmetic sequence or something like that, and that the way to do that is to just write the numbers backward on the second line and add them up and multiply by the number of terms and divide by 2, then you must be as great as Carl Friedrich Gauss. You must have the potential. You just inform us and we'll nourish it further. Now what happened is, when he grew up, during his time, everybody was obsessed with the fifth postulate of Euclid. Euclid has 5 postulates.
Sir?
Sir, nawara.
Wala po, sir.
Yeah, I know, I'm still here. Going back. During the time of Carl Friedrich Gauss, people were trying to prove the 5th postulate of Euclid. The 5th postulate of Euclid was one of the 5 postulates. And they were trying to prove the 5th using the other 4. Okay? So that was the work. How did they do it? Remember how you did proving in logic and set theory? That's the same thing. You're trying to arrive on the 5th postulate by beginning on either of the 4 and using the rest of the 4 as probably your middle line. From then on, Gauss already knew that there's modern geometry. He has already worked on modern geometry. He has written his paper, but during his time, no one would believe him. It's like the time of Galileo. No one would believe that that the sun is the center of the solar system. Earth was. That's a predominant belief. And what happened to Galileo when he put forward the idea that the sun is the center of the solar system? He was ostracized. So he doesn't want to offend everyone. He doesn't want to go against the common knowledge of his time. What he did, because he was reluctant, he kept his paper. He kept his paper and research to himself and never published it. That was during the 1800s. Now, years after, there are 2 great mathematicians in the name of Lobachevsky and Bolyai. Lobachevsky was a Russian mathematician and Bolyai was Hungarian mathematician. Now, the 3 of them, I need to punctuate first. Gauss was German, Lobachevsky was Russian, and Bolyai was Hungarian. Although Russia is partly Asia, if you notice, the three foremost people who founded modern geometry are all European of European descent. Now, after years, Lobachevsky in Russia and Bolyai in Hungary independently discovered modern geometry around 1830. Of the two, though, Lobachevsky was the first. And while they were finishing their paper, they were trying to publish, it became clear to them that Gauss already discovered it years ahead of them. This was the story of that. Janos Bolyai had a father, Wolfgang Bolyai, and like many mathematicians before, Wolfgang worked also on the fifth postulate. Now, Wolfgang, because during those times, there are few mathematicians and academicians befriend themselves, like mathematicians friend other mathematicians to extend his network and his knowledge. So Wolfgang is a friend of Gauss. And for years, he has tried to discourage Janos Bolyai. According to him, stop working on the work of Euclid anymore because I've wasted my time doing it and I amounted it to nothing. But Janos Bolyai, being obstinate himself, worked on the fifth postulate, and in the process, he discovered modern geometry. He wrote a paper on it, and Wolfgang, being a proud father, told Gauss about it. And he said, it's not really the exact words, but probably he said, "Hey Gauss, you know what? My son is so great. He developed a different type of mathematics. It's called modern geometry." And Gauss said confidently, "Modern geometry? I already know everything about it many years ago." When Janos Bolyai found about it, he was so frustrated, he stopped pursuing the work. He was frustrated because he thought all along he was working on something original, and only to find out in the end that it's just a work that was already finished by Carl Friedrich Gauss. But in his small town, while Bolyai has already been discouraged, Lobachevsky was doing his work. He finished his work. And Gauss heard about it. Gauss became so curious about the work of Lobachevsky on modern geometry that he purposely, according to the story, he purposely learned Hungarian just to understand the modern geometry take of Lobachevsky. Now, before we proceed, because we've been mentioning about the 5 postulates of Euclid already, let's talk about them first. It will be instrumental in your learning of modern geometry if you'd be able to understand them as early as now. Now, what I'm going to do with the postulates is I'm going to simplify them, give you an equivalent of the statement that we would be able to learn in one sitting too. But along the process, because the 5 postulates are so important in your journey for understanding modern geometry, we're going to dig deeper into them in details in their original statement. Now, the first postulate says that if you have 2 points, I'm going to draw 2 points here. Let's say you have 2 points in a surface. According to Euclid, you can always draw a unique line between them. So here. So whenever you have 2 points, You can always connect them to create a unique line between them. When we say unique line, it means there is only one line that could connect 2 points in a uniform field or plane or space. Again, the first statement is there's only one line that connects 2 points. The second postulate states that if you have a line, it sounds more like an extension of the first. If you have a line, you can always extend them both sides indefinitely. That supports a statement that a line extends both sides infinitely. That's the definition of the line, by the way. So whenever you have a line, however big or small, you can always extend it on either side. The third statement, now you must be wondering by now, why are these statements simplistic and obvious? That's the point. These 5 statements are axiomic in nature. You don't need formal proof to prove them because they're so obvious, you can easily spot that they're true, unless you use a different type of geometry to disprove them. The third statement is, if you have a and a radius, you can always create a unique circle. That means if your radius is 3, the circle that you could create is unique to that if your radius is 4, and so on and so forth. The fourth statement states that all right angles are congruent, essentially the same. So the right angle in Ira's place is literally the same as the right angle in Katrina's place. If Ira is going to try to measure it, it will be 90 degrees. And if Katrina wants to validate it, it will be 90 degrees. In all essentiality, they're the same. Now, the fifth and the most controversial of these postulates states that if you have a line and if you have a point away from the line, the reason we're saying away from the line is because the line is a collection of points. So it must be outside the line. If you have a line and a point outside the line, then there is only one line that you could draw that is parallel to that line. Or we could say, if you have point A and line L, then you could only draw one line through point A parallel to line L. When we say parallel, a line that will not meet or intersect with line L, even if we extend the line on both sides indefinitely. That's basically the definition of what's parallel. And over the course of the work, these mathematicians have tried to prove that there is only one line that could extend, that one could draw that is parallel on the other line. Now, along the way, these mathematicians, Carl Friedrich Gauss, Nikolai Lobachevsky, and Janusz Bolyai, in their investigation, found out that on a different situation, there could be infinitely many lines that you could draw that is parallel or non-intersecting with that line, especially if your geometry is non-uniform geometry. And that paved the way. The efforts of these mathematicians to prove or otherwise discovering that it can be disproved by a different type of mathematics paved the way to the discovery of modern geometry. Now, Gauss realized while attempting to prove the fifth postulate from the other four, that there could be a different geometry like Euclid, but might not be a line through a point that doesn't meet a line. So it's like Euclid, but it's different. It was unclear. It was unclear first in the work of Lobachevsky, but Gauss started developing this geometry. That geometry that was essentially discovered was the geometry in the surface of a sphere, or what we call the spherical geometry. And if you're going to notice spherical geometry, if I'm going to draw a sphere here, notice that in the sphere, all of the elements of a classical geometry can be demonstrated in a sphere. For instance, there is a point on the surface of a sphere that could also be the same point as that of a uniform plane. There's also a line, but in the definition of a line in modern geometry, particularly in spherical geometry, a line is called a great circle. And it doesn't extend indefinitely. It ends because it has limits as to how much it could extend. Basically, it's a circle. It's like if you're going to cut a plane through a sphere, if I'm going to cut it here, let's say you force a plane through a sphere, you're going to form a circle. And that's basically a line. Remember a globe where it has longitudes and latitudes? These are the lines on the surface of a sphere. But if you're going to extend them further, you'd notice that you'd go back to your point of origin, thus giving you a circle instead. In the mathematics of a spherical geometry, a line is called a geodesic. It's basically a curved line forming a great circle. There's also angle in a sphere, but the angles formed on the surface of a sphere follows a different rule than that of a regular plane. For instance, the triangle that can be formed on the surface of a sphere may exceed a sum of 180 degrees. It could be a positive curvature triangle or a negative curvature triangle, as opposed to the regular triangle of a plane. Now, these positive curvature and negative curvature triangles, we call them geodesic triangle because their sides are geodesics. Their very telling property is the sum of their internal angles exceed 180 degrees. Or it could even be less than 90 degrees in the case of negative curvature triangle. Now, Lobachevsky and Bolyai worked on the same geometry at the same time. Lobachevsky was ahead of Bolyai, though, and Bolyai was discouraged because he found out that Carl Friedrich Gauss knows about it. But of the three of them, only Lobachevsky was able to publish it. It's probably one of the many failures, one of the most significant failure of Gauss, because he was reluctant. He doesn't want to frustrate other mathematicians, so much so that he did not publish his work. Somebody else did, and that's Lobachevsky years after Gauss found about it. Aside from, so I'm going to show you the faces of these famous people because I've been talking without showing their faces. This is the introductory video of the German movie To Measure the Earth about Gauss. If we're having face-to-face class now, this is a movie time. We usually watch this movie as part of the class. But sadly, I cannot compel you all to watch the movie because it would consume a lot of your data. So instead of, I don't know, maybe I'm going to share with you the link. Let me know via the in-call messages if it's necessary for me to share the video via the Google Class, either the video or the link, because I'm going to do it if you ask, so that some of you could, probably get entertained with the life of Friedrich Gauss. This one is Nikolai Lobachevsky. Look at him. He looks very angry in the picture, brave. He grew up in a poor town in Hungary, and he grew up mostly poor, but he was intelligent. And he did not learn English or German. So Carl Friedrich Gauss learned his language in order to understand his work instead. This is the frustrated Janus or Johann Bolyai, son of Wolfgang Bolyai. Wolfgang is the inspiration of the famous software Mathematica. Mathematica is the best software if we're gonna do computation or graphing in mathematics. Only that, while it's very powerful, it's also not free and it's expensive. So for mathematicians, we content ourselves with the cheaper software, MathCAD or GeoGebra. But if you have the money and if you want visualization that's powerful, that enables you to do Python programming, you do Mathematica. Now, before we had a technology mathematical teaching and we learned about it, but the curriculum changed and, Okay, so those are the three famous people that we just talked about. The rest, we have Eugenio Beltrami, Italian, also. I lost. Okay, so did you see Eugenio? Eugenio Beltrami? Eugenio Beltrami is Italian. Here. And the next one is, we have Felix Klein. I think it's German. And the last mathematician is, I don't have a picture. I'm sorry. Maybe you can search for the picture. The last one is a French mathematician. His name is, lucky for you, we're having French class. And the correct pronunciation of this, Henri Poincaré. Henri Poincaré, not Henri Poincaré. That's, that's a wrong way of pronouncing it. Henri Poincaré. The three of them worked by extending the works of Carl Friedrich Gauss, Nikolai Lobachevsky, and Janus Bolyai. Now from the spherical geometry, other geometries that are non-Euclidean arose. By the way, some mathematicians remark how frustrating it is that for the past thousands of years, we have been studying spherical geometry, but we did not realize that it's a mathematics distinct from Euclid. Ptolemy studied the heavens when he studied the planets, the heavenly bodies. And if you're going to look at the sky, literally, the sky is spherical in nature. It's like a surface of a sphere, but this time you're looking from the inside. And basically what they're doing is they did measurements, they did mathematics to approximate the distance of one object to another, and that's basically spherical geometry. In this course, given that we are under pandemic and given the difficulty of studying everything with the constraint of time, we're mostly going to focus on spherical geometry, hyperboloid geometry, conic geometry, and hyperbolic plane geometry. That would be for advanced mathematics. We're not going to talk about it. But at least in the spherical geometry, we're going to talk about distances of one place to another on a surface of a sphere using only coordinates. We're going to measure distances from one crater to another, for instance, of a moon, using only the data from NASA on their coordinates. We're going to approximate the distances. Let's say from your place to, let's say, a famous place like what famous place is it? Like the Mayon volcano, for instance, using only the coordinates from the internet. So it may sound like it's simplistic, but we're going to use matrices, we're going to use a little bit of calculus in order to finish the computation. Although nowadays you can easily use Google Maps to immediately get the distance, it's always helpful to know the computation behind them, and so on. We will have lots of manipulation on the surface of the sphere. Now, of the three here, the extension of the spherical geometry was begun by Eugenio Beltrami, and he did it by generalizing the sphere. You remember your mathematics in high school or your classical geometry, if it was included in your lessons. A sphere's equation is sorry. What's the sphere's equation? Yeah, before I write it on the slide. Anyone who remembers the equation of the sphere? Clue: the unit circle is x squared plus y squared is equal to 1. So a sphere could be similar to that effect. Anyone who remembers the general equation of a sphere? Write it in the in-call messages. For motivation, +3 participation points for those who can remember the general equation of a sphere. I'm giving you 60 seconds. While we're waiting for your answers, I'm going to type down the pronunciation for Henri so that you would, remember it. It's a pronunciation of Henri Poincaré. That's the name of Henri, or Henry in English. Anyone who remembers the general equation of a sphere? No one? Going once?
Sir,
Going twice?
gina-type ko.
The general equation of a sphere is...
Sir.
Yes, friends? You're typing it?
Sir, try, sir.
Okay.
Sir, try.
Yeah, John Lulu, that's correct. Somehow. That's 2 points, though. +2 participation points. Regina, yes? You're raising your hand.
Yes, sir. X minus
Angelica,
a
that's
squared
almost
plus y wait, sir. Close and open parenthesis, x minus a squared plus close and open parenthesis, y minus b squared plus z minus c close and open parenthesis, square.
Hello, sir.
Yes, thank you, Regina. That's last one. Yes, friends?
Same as Regina, but it has different in tawag sa niyo, pagbigkas po. The quantity of
Okay.
a minus a squared plus the quantity of y minus b squared plus the quantity of z minus c squared is equals to r squared.
Okay, thank you very much, friends. Now, let's reveal the correct answer. Now, for a unit sphere, it's generally x squared plus y squared plus z.
Nawara si sir?
I'm still here.
Ay,
Okay.
sorry po.
Okay, going back, it's x squared plus y squared plus z squared equals k, where k determines the size of the circle. It's basically the radius. The larger the value of k, the larger the circle is, the sphere is. Less than 0. Like -1, -2, -3, then the sphere cannot exist. Because where would it reside? You know, after 0, after nothing, where will it exist? Maybe on the other dimension, not in this dimension. If we're going to draw the sphere. Now, going back, Eugenio Beltrami generalized the sphere, and he found out that if he is going to change one thing on the equation, a different type of modern geometry arises. Now you have to remember that the first type of modern geometry that was discovered was the spherical geometry. So I'm going to write it down here so that you can use it for comparison. So the first, keep going back on that picture of family. So the first one is spherical geometry, where our goal is to investigate what happens on the surface of a sphere. Okay. Second is Eugenio Beltrami changed the general equation of the sphere. And what he did is only change one sign. Very simplistic, very small change, but it changed the entirety of the interpretation of the spherical geometry. It became x squared plus y squared minus z squared is equal to k. For values that is equal to 0, if k is equal to 0, I don't know what's happening. It keeps on going back here. This guy wants to be seen. Nulls. Okay. So if it's k is equal to 0, what we form is, if we're going to draw the XYZ plane, is a cone. A cone here. So this cone is the result of reversing the sign on the z. And the modern geometry involving the cone is a geometry involving the surface of the cone. Now, we can draw triangles on the surface of the cone. We can draw lines on the surface of a cone. Each of these things have their own interpretation when it happens on the surface of a cone. The third type of geometry is when k is equal to 1. And when k is equal to 1, it forms a different type of geometry called a hyperboloid. I need to take note of this because I don't know, maybe I'm going to lose it. Or maybe because it's not part of this slide. This one is conic geometry. Now, hyperboloid is like this. It's like a tube. So that's hyperboloid. And the fourth one is, now hyperboloid happens when k is equal to 1. Now when k is equal to -1, what happens is we have a hyperbolic plane. So this one is a plane, this one is a plane too, and they're not touching each other. This plane has finite size, but the surface goes infinitely. Like from here, you can go to the side. You can only approach the side, but you can never touch it. Okay? So I'm going to show you, I'm going to stop my presentation here. And then I'm going to show you the different geometries when they're rendered using computer. Whiteboard so that we can write on the, on the surface. We're about to end our lesson though. So far, can I get your opinion on modern geometry? Is it something that you could like, or does it sound boring? What's your opinion on it?
Maganda siya lang sa history.
History, yeah.
Yung history sa
Yeah.
mga mathematician,
History is-
nag-enjoy ako dito.
Yeah, history is only like introduction.
Kaya gan sir, pero ang topic sir, history gid ako sir.
Okay, maybe you need to consider changing major. What?
Pwede. Pwede.
Yeah. So the first one that we're going to talk about, we're going to see is a sphere. I'm going to show you a sphere so that we could try to check whether we could draw a triangle on its surface or not. Only problem is here. So it's black. I hope you can see your screen now. Although the picture that we have is black. Can you see it? Can you verify? Now look at this. on the surface of the sphere, you can draw a triangle. And that triangle will have this, we have properties too. Just like, just like a regular one moment. I'm trying to exit a window.
Hello, sir.
Yes?
Ma-clarify ako.
Okay, sure.
Sir, those students who give you the formula of the sphere ba ito, gintagaan ko po 2 points.
Participation, yes.
Opo, pati sa chat box po.
Okay, sure.
Okay
That's
po,
very
thank
good.
you.
Now, let's have Franz.
Yes, sir.
Okay, thank you very much, Franz. Let's have an overview of geometry of the sphere. Look at this. Similar to the regular, the uniform plane, we can draw a triangle here. And the triangle could have angles as well, like this one. You can also draw a point. If you're going to look at the globe, on top of the globe, on the North Pole, there's a point. At the bottom of the globe, there's also a point. You would notice that all of the longitudes would connect the point on the North Pole Regina, I'm still here. Don't worry. Can you hear me?
Yes, sir.
Hello?
Yes, sir.
So going back, now notice that the globe is a manifestation, the first proof that you can draw many lines between points. Because in the globe, the first point would be in the North Pole, the second point would be in the South Pole, and you would see that the geodesics, the longitudes, all of the longitudes would intersect both points. I'm sorry, this doesn't look like a sphere. I'm gonna erase this because this is embarrassing. But the point is, in a circle, in a sphere, it looks more like an oblong. I'm sorry. You would see that a lot of lines could be drawn at the same time. In fact, an infinite number of geodesics can be drawn to demonstrate that there's an infinite number of lines that can be drawn connecting 2 points. And that is in the surface of a sphere. Also in the surface of the sphere, you will have this type of figure. And you'll also have, a different formula for the area of a triangle. A lot of computations will change. This is, if you're going to look at it, this makes the entire spherical geometry a totally different discipline. I'm going to show you the conic geometry formed when the modified general equation of a sphere of Beltrami is set to k is equal to what value of k again, if you remember? What value of k results in a conic geometry? Anyone?
0.
Sir.
Sir.
Sir,
Zero.
sir. Zero.
Zero.
Sir.
One moment. let me read the-
Zero. Zero.
Who was that again? Okay, that's correct. If the value okay, if the value of k is 0, it will give you a cone like this one. This is an example of a cone. See? And at the center of this conic geometry, I think this is a dimensionless point. Okay, and the surface of a cone, you could still draw some triangle, but to be very honest, I'm not familiar with conic modern geometry. This is a very higher mathematics. Okay, so let's proceed with hyperboloid. Hyperboloid happens at what value again?
1.
A is equal to 1.
1.
This is what a hyperboloid looks like. Can you identify a real life object that closely resembles a hyperboloid? Do you have something in mind?
Yes, sir.
What is?
Sir. Ako, sir.
Yes?
Embudo.
A funnel. That more resembles a cone, right?
Uga, sir.
Chinese yo-yo, sir. Sir.
What?
Sir,
Chinese yo-yo.
Chinese what?
Chinese yo-yo.
A
Yung,
Chinese
sir,
yo-yo.
Yeah.
Yes, somehow.
Sir, ang sa mixer baga, sir. Ang sa
Somehow,
plantation
yes.
pa, sir. Ang sa plantation. Sa mixer. Yung maglabas na sa
tapos
utak.
sir, in-answer ng inapurunan San PC.
Mhm,
Ang
yeah. Yeah, it looks
Ang-
like it. A
plantation, sir.
megaphone. How about the exhaust of a nuclear power plant? Looks like
Yes, sir.
hyperboloid as well. Okay.
Well, sir, sa
And the
plantation.
third one, I think the third one that I'm going to show you, the hyperbolic, for me, is the most interesting. I don't know about other mathematicians or other mathematics teachers, but for me, the hyperbolic plane is the most interesting of the three. The reason for that is, one moment, I'm going to show you. I'm going to show you only the bottom part of the hyperbolic plane. You can, this is the bottom part of the hyperbolic plane. If we're going to add the upper part, all we need to do is just to flip this, like this, and we'll have the upper part. So, yeah, that's the upper and the lower part of a hyperbolic plane. Just to demonstrate that there are two parts, the upper and the lower portion. I'm going to remove the upper part so that we can focus on one hyperbolic plane at the same time. So a hyperbolic plane, for me, looks like a convex lens. I'm going to emphasize hyperbolic plane begins and ends here. So the hyperbolic plane is basically here. Sorry for the excess line, just so I could draw in the image. The hyperbolic plane is mostly just this. This is the hyperbolic plane. It looks like a convex lens. Now, what's interesting in this type of plane, what interests me about it, is the fact that you can move from the center here to here. You can travel indefinitely but you're never gonna touch the end. I don't know what happened while there's a triangle here. So you could travel to the end, but on this edge, you can never touch it. This edge is basically like an asymptote where you can only approach, but you can never touch. So what happens if you look from the top and you will have images drawn on its surface? I'm going to show you a famous artwork using the hyperbolic plane. This was the cover of the book of Philip Zimbardo in his book. There's a book called The Lucifer Effect, but I cannot find the exact image. So here. So I'm going to show you an example of an artwork. Of a hyperbolic plane from above. This is an example of a hyperbolic plane from above. This is an artwork. It's like an optical illusion. If you look at the black part, you will see the devil. If you look at the white part, you will see angels. And you would notice, okay, I'm going to ask you, what do you notice about the pictures as they get nearer and nearer to the edge of the hyperbolic plane? Anyone?
Para silang ano, sir, mula sa taas
Nag-small,
pababa.
sir.
May ano sila, may
Regina?
pattern.
Was that you?
Smaller
What did you say?
material to bigger material.
What do you notice, Regina? The pictures? What do you notice about their size as the pictures move towards the edge?
Picture becomes smaller and smaller.
It becomes smaller,
Exactly.
sir.
They become smaller.
Tuna sir sa dako pa
But-
tayo.
Yeah. But they don't approach the edge. That is the most interesting aspect of a hyperbolic plane. Now you're wondering, what are the applications of this modern geometry? Why do we need to learn modern geometry? Remember the story about Newton. We're about to end our lesson, and this is our end story. Remember the story of Newton. Newton was supposed to, story goes that he sat at the bottom of an apple tree and an apple fell before his eyes. And then he realized the apple fell because of the action of the force of gravity. From then, he was able to generalize the movement of objects in the universe using the concept of gravity as a force. And he said that the pulling force of a gravity is directly proportional to the distance of an object being pulled to the center of the object, in this case, a planet. Now, years later, Albert Einstein came with two most important works. We call them now the general theory of relativity and the special theory of relativity. And according to Einstein, gravity is not a force. Gravity is a consequence. Imagine if we have a plane as a space, if our space is plane, like this one, and uniform, and you put a very heavy object on top of it, then the plane is going to curve. This one. to accommodate the mass of an object. Now you need to remember, I'm not very good in drawing, and you need to remember that when we say space, we're actually referring to a grid of space and time, or space-time. And according to Einstein, very heavy objects like the sun and the earth curve space and time. And this curvature around them makes all of the objects fall. I'm going to show you an example. I don't have an example for that. But what happens is, instead of the sun pulling the earth close to it, to itself, or the earth pulling on you, the curvature of the space around the sun allows the earth to fall into it. And the curvature of the space around the earth allows us to fall into it, creating a gravity well. We are falling because of the curvature of the space-time. And if you watch the movie on Interstellar, it was demonstrated there very well. Interstellar revolved around space travel, and there's a scene there where they worked on a spaceship near a black hole. If you remember, a black hole is so massive that its gravity is so strong that no light can escape it. So if it's so massive, then the curvature of the space around it is so steep as well. You notice, while everybody was getting old, the person on that spaceship was young, right? So it also influences time. Near very heavy objects, time slows down. Not just gravity becomes very strong, but time also slows down. So this type of physics, this type of theory of Einstein, the only mathematics that could support it is a mathematics on the curved surface. And that is the primary use of modern geometry. Now, if you're planning to be an astronaut in the future, or a scientist, or if you believe that in the future, this type of knowledge is so common because we're so advanced, and you want to participate in that kind of future, I think modern geometry is for you. You need to learn that that the space is not always uniform. That there's a region in the space that is either positively or negatively curved, and that in order for you to have an accurate measurement on those spaces, you need to use a Hello. So going back. So again, that ends our discussion on the introduction on modern geometry. In this class, we're mostly going to focus on spherical geometry. We're going to familiarize ourselves with the formulas involved,
Yes,
with how to compute for the internal angle of a triangle, with how to compute for the area of a triangle. We're also going to talk about the vector, the direction of the forces. We're going to talk about matrices. And then we're going to proceed with computations on the surface of the geometry. Yes, Regina, we're almost done. Now, before we end, I'm going to entertain your questions. Is there any question? I hope you took some notes, because after this, either this evening or on Saturday in the weekend, I'm going to post a quiz regarding the history of the modern geometry. I hope you took some notes. I hope you took some screenshots. I'm going to post the recording of this on YouTube, so watch out for it on my YouTube. I hope you review the video, because ideally this is one of, since this is introduction, it will be a simple quiz, and I hope you perfect it. So we're gonna have a quiz. Any question though?
Wala naman po.
Christine, yes, thank you. Okay, so would you like to, you know what? The reason I punctuated that the proponents of modern geometry, all 6 of them are from Europe, is because I want to encourage you. I always believe that in a certain crowd, like your class, there are some students who have the potential in the future to discover existing mathematics or contradicts an existing mathematics altogether. One that is a key player, a game changer. Try to explore, try to ask, observe your universe, your surroundings, ask questions that mathematics could generalize. Ask yourself, is there a mathematics that exists that could help me compute for this? If there is none, maybe it's time that you develop it. And if you do, then it will be a proud moment for DEBESMSCAT that one of its products has amounted to becoming a mathematician that could go down to history. Since there's no question, thank you for listening to the discussion. Franz, please post the names of participants in the Google class.
Yes,
So
sir.
that others may verify.
I have
Let's
the
now take
screenshot
pictures.
of the chat.
Open your camera so that we can have. Thank you, Franz. Please open your camera so that we can take a picture
Ay,
as proof of your attendance.
Hi, sir.
Haggard na ako.
Wow, Christina.
Sir.
bled ako, sir.
Sir.
Wow. Yeah.
Excuse me, sir.
Laban daw.
Haggard as a
Una-una
career
nun
or
ako sa...
haggard as an accident?
Excuse me po, sir.
Yes, you're excused.
Dapat, sir, pag kami nag-open cam kami, sir.
Hala, ito na sa likod. Paano ba pagpa-front?
Diba niya, baka na nagawaran.
Ancam.
Hello, Christine.
Paano ba pagpa-front sa ancam?
A moment. Also, are you going to take a picture as well? So that we have something to post on Facebook. To encourage others to, join. Take pictures. Wow. Mitch, you look beautiful. Congratulations. Ira, you look angry. Why are you
Hindi, sir.
Ora pa na ko, sir. Di
Wow.
ako pod na balay.
Hi, Ira!
Tayo, kaya na.
Ivan Jun, you look like a mess. Thank you very much for attending. I really appreciate your help. And this class is officially dismissed. Thank you. See you next week.
Grabe rin
sir.
po.
Naka-open yung
Yun ang bawat
Nag-selfie na lang ako kay di ako mara magpa-front sa ancam.
anak ko.
Ato talaga siya sa likod.
Pinituwa.
Grabe no ran sa amon.
Sa amon, pikawranan pa lang.
Ano pa siya?